So here's a note for you. We are not able to find uppercase f of x always. That's why we have those methods to approximate. Here's an example. The integral from 2 to 3 from e to x to the third dx, no human being can find the uppercase f of x. No one. It exists, but no human being can find it. We will be able to approximate with whatever, n equals 4, n equals 8, whatever number of subintervals. But we're not capable of finding the antiderivative and to find this exactly. The calculator will, and it will do the same thing. But please understand and remember that we are not always able to find the most general antiderivative for every function. So please remember that. Okay, next, I wanted to talk about the properties. Properties of the definite integral. And the definite integral has many properties. We already know one of them. The integral from a to b, a to a, from f of x dx. We already discovered this a few minutes ago. I'm going to call this 1. Here's the second one. The integral from a to b from f of x plus g of x dx. And it could be negative. It could be a subtraction. What do you think this equals to? Same for the limit, the same for derivative, the same for the summation notation. What will this equal to? What do you think?
F prime.
No, this is the integral. So the same property, the integral from a to b from f of x dx, either positive or negative, depending on what we have. The integral from a to b from g of x dx. So it was we used the same property when we differentiated, right? When we differentiate the sum, we had the derivative of the first function plus the derivative of the second function. So the same for the limit and the same for the integrals. And the same property for the summation notation. Is this okay? Yes? No?
Yes.
Property 3. The integral from a to b from f of x dx is the same with the opposite by swapping the limits of integration. Please remember this is a very important property. F of x dx. So if I swap the limits of integration, I have to put the negative in front. Here is another one. Still common sense because we used it before several times, even tonight. Property 4. The integral from a constant times a function, f of x dx. What do you think happens here? We had the same thing with the limits. We had the same thing with the derivative. We had the same thing with the limit, with the summation notation. All the same.
Is it just the constant times?
Of course, exactly. Makes sense. The definite integral from f of x dx. Property 5. Now, if I have the integral from a to b from f of x dx. So here's the interval, a to b. And somewhere here I have c. This is the same thing with the integral from a to c from f of x dx, plus the integral from c to b from f of x dx. Can I have more than one point? Yes, as many as you want. The area under this, the graph between A and C, plus the area under the graph between C and B is the area between A and B. So we can split the integral if we want in as many pieces as we like. Okay, number 6. For a positive function on the interval a comma b, the integral has to be positive. Now, property 7. Let's say I have a function like this. Here's f of x. Here is g of x. Of course, this is a and this is b. In my picture, f of x is greater than or equal to g of x. Fine. I can apply integration to both sides from a to b. So if the relationship between f of x and g of x is this one, f is above g, f is above g, then the area, this area, will definitely have to be greater than this area. So the area under f, from a to b from f of x dx, must be greater than or equal to this area. If f of x is above g, the area here has to be greater than the area under g, which makes sense.
I have a question.
Yes.
Sorry to stop you.
No, I wanted to.
I just realized, since we are talking about area, is there supposed to be some sort of like square units on any of these?
Yes. Yes. So, but you don't have to write it because it's abstract, but yes, there will be units squared.
Okay, but we wouldn't need to write it.
No, unless this problem specifically says miles. Then you will say miles squared.
Okay.
Correct. Very good. Property 8. And remember, there is no integral if the function, no definite integral if the function is not continuous when we apply the fundamental theorem of calculus. Please remember that. Okay, property 8. Let's suppose we have two situations simultaneously. Symmetric interval. That's situation 1. Two situations have to happen at the same time. Symmetric interval? What does that mean? Well, negative a to a. Negative 5 to 5. Negative 2 to 2. This is a symmetric interval. And even function. How does an even function look like?
Wouldn't an even function automatically have a symmetric interval?
Say it again.
Wouldn't an even function automatically have a symmetric interval? Because like even has
No, because
symmetry with
I may be asked to find the integral from negative 3 to 3 from x squared dx, but I may be asked to find the integral from negative 4 to 10 from x squared dx.
okay.
So if both conditions happen, symmetric interval and even function, because this is an even function, but the interval is not symmetric. So this is not applicable here. So let's see what happens. So in this case, for an even function, so the integral from negative a to a from f of x dx, when f of x is even, notice what happens here. These two pieces are equal. So it's easier if we write twice the integral from 0 to a from f of x dx. This is easier to calculate. And this is allowed. Why? Because both conditions are fulfilled. The interval is symmetric and the function is even. Now, property number 9, same thing but when the function is odd. Here's an odd function, like x cubed is an odd function. Here is a symmetric interval between negative a and a. So now let's see what will be in this situation. The integral from negative a to a from f of x dx. Both conditions are fulfilled. Symmetric interval, but the function is odd. What do you think the answer would be? I want to give you a hint. This is a positive area, and this is a negative area.
Would the area equal 0?
Yes. Thank you. They are equal, but one is positive and one is negative, so when I add them, I get 0. Very convenient. Very important to remember. I promise you the last property now. Property 10. So let's take a look at the following scenario now. We have a small number. Positive, negative, it doesn't matter. Lowercase m. We have a big number. Uppercase m. And we have a function prancing along, f of x. From my graph, it's very clear that m is less than or equal to f of x, less than or equal to m of x, uppercase m, I wanted to say, from a to b, of course, on ab. All right, here it can go up or down, I don't care. I only care about what happens between a and b. Is it clear that this area will be smaller than this area, which will be smaller than this area? Very similar to a previous property, very similar. All I have to do is just put the integral symbol. So if that's the situation, then the integral from a to b from little m dx is less than or equal to the integral from a to b from f of x dx. Remember, there is no integral without dx. These two pieces go together at all times. Less than or equal to the integral from a to b from uppercase m dx. We can, and we are able to determine these. M is a constant outside. Which function prime is 1? Give me a function that we differentiate to get 1, because once I move this here, there is only 1 left. Which function prime is 1?
X.
Very good. From a to b. Less than or equal to the integral from a to b from f of x dx. The same way, mx from a to b. Finally, here, I plug in b and I subtract when I plug in a. Subtract b minus a. This is, as I promised, the last property. Okay. So let's look at some applications here. Back to 5.2. Properties of the definite integral. That was the strangest thing. It was recording audio but not video. The video was stuck on some previous page. Unbelievable. I'm glad I noticed. I want to look at the property and then we can look at those graphs. No problem. I promise to show you those, the last two here. So let's choose 53 or 54. Okay. So we have the integral from -2 to 2 from f of x dx. And they're telling us that f of x is a piecewise defined function. And it's given to us as 2 from -2 to 0. And 4 minus x squared for between 0 and 2. Okay. So in order to determine the integral between -2 and 2 from f of x dx, I realized that there is a break at 0. So between -2 and 0, this is the function. And between 0 and 2, this is the function. So the splitting property works perfectly here. So from -2 to 0 and from 0 to 2. From -2 to 0 plus from 0 to 2. So we are using property 5. So then I will write equals the integral from -2 to 0 from something dx plus the integral from 0 to 2 from something dx. What do I write here and what do I write here? Anyone? It's okay if you're, yes, Aaron?
Sine and one of them is cosine. Or like, what other functions are with each one?
Yes. So which function do I put here?
I forgot what they look. I forgot what they are exactly. I don't see what it's here.
Between -2 and 0. Which function do I put here?
Oh, 2.
Right? And between 0 and 2, which function I put here?
4 minus x.
I know it's silly, but I just wanted somebody to say it. That's it. That's all I need to do. And now I just perform the calculations. So which function prime is 2? Very good. From -2 to 0 plus. Which function prime is 4?
4x.
Very good.
X to the power 3 over 3.
That's it. Done. So now I plug in 0. When I plug in 0, I get 0 minus. When I plug in -2 plus. Luckily, I don't have to plug in 0. I will only have to plug in 2. 4 times 2 is 8. minus 8/3. Because when I plug in 0 there, these are, this is a polynomial. When I plug in 0, I get 0. So positive 4 plus 8, 12, minus 8/3, so times 3, 36, minus 8, divided by 3. So that is 28 over 3. And that is the integral from negative 2 to 2 from this piecewise defined function. It has a break at 0. I had no choice. From negative 2 to 0 and from 0 to 2. And we use property 5.
But we could only do that since it was still continuous. If that
Yes.
first one did not have or equal to 0, we just would say not
It's a very,
equal.
yes, so 2 is continuous here. 4 minus x squared is continuous here. So even if, it's a very good question, perfect question, thank you. Thank you. So when I have a piecewise defined function, it can be like this. A, B, and C. So this is f of x. This is one piece, and this is the other. So then the integral from a to c from f of x dx will indeed be the integral from a to b from f of x dx plus the integral from b to c from f of x dx. That's one option. What if I have this situation? It's exactly the same. Because
But I thought we could only use this if it was continuous.
Yes, the function is continuous on AB. And this function is continuous on BC.
BC, but it doesn't have to be continuous.
It
from
doesn't
A to
if it's a piecewise defined function, and this is, in this example, at 0, this is negative 2. But this one at 0 is 4. So this one here is 2, and this one here is 4. It doesn't matter. This one, this function is continuous on AB, and this function is continuous on BC.
Gotcha.